This worksheet's going to help us practice ranking alkenes in order of relative stability. We're going to start by drawing the structures of cis and trans 2-butene, and then we're going to rank them in terms of stability, and there's some hints here that we can use to things that we can think about while we're ranking them. So initially, right off the bat, you might be thinking, hey, I do not know how to draw cis 2-butene. We have not yet gone over alkene nomenclature, so we haven't learned how to interpret the names of these molecules and how to draw their structures. This is going to happen from time to time. You'll see a name of a molecule, you'll need to know its structure, and it's something that we haven't gone over in class yet. In that case, all that you have to do is just Google it. The internet is a really great resource for IUPAC nomenclature. So just typing in cis-butene, most likely it's going to take you to Wikipedia, because Wikipedia is a great resource for chemical structures and various facts and things like that. And this is actually giving us the structure of both cis and trans 2-butene. So what I'm going to do is draw them on this page over here. I'm going to draw them in line notation instead of, that's like a condensed, partially condensed notation. And then what we're going to do is rank. We're going to start, like the worksheet asks us to start, by just ranking these two alkenes. So we're just going to rank these two relative to each other. And we've talked a bit before about how when we're comparing the stability of alkenes, the first thing that we want to take into consideration is steric hindrance. If we're looking specifically at the double bond, we want our substituents, the largest substituents in this molecule, to be on opposite sides of the double bond, which gives them lots of room to spread out. So a trans alkene is always going to be more stable than a cis alkene. I think I'm just going to kind of put them in the middle of this. So sort of like that. This will be our initial ranking. Cis alkenes are always less stable. So now let's go back to the instructions and see what it's asking us to do next. Next, it wants us to look at ethene and 2,3-dimethyl 2-butene. So we're going to just continue to use Wikipedia here. I'm going to enter in ethene and see what that little guy looks like. Oh, it auto-corrected me. So I'm going to try again. Ethene, this looks like, we can see it's a 2-carbon alkene. That's kind of funny to draw in line structure. So in line structure, it looks like that. But that, like, for whatever reason, it weirds me out. So I have to draw the carbons in there. So there's ethene. And the other molecule that we're going to be adding is 2,3-dimethyl 2-butene. So let's look that up. Thankfully, a lot of these are really common molecules. So just by typing 2,3-dimethyl, you can see that 2,3-dimethyl 2-butene is like one of the most common searched things. So we can pull that guy up, and that we can see that's an alkene. We'll draw this guy that has methyl groups. 4 methyl groups on the double bond. And so what we're going to do next is add these two molecules into our relative ranking of stability, and let's see what kind of hints it gives us. So looking at this, how are these new molecules different from the cis and trans 2-butene, and how are they different from each other? What do we know about carbocation stability? So one of the things that we know about carbocation stability is that the more alkyl groups you have on a carbon-carbon double bond, the more stable the molecule is. So just in terms of these two, if we're looking at just these two molecules all by themselves, a carbon-carbon double bond that has 4 carbons attached to it is going to be more stable than a carbon-carbon double bond that has 0 carbon atoms attached to it. The more carbon atoms we stick onto this double bond, the more stable it is. So we know that this alkene is more stable than this alkene, so I'm going to kind of separate them like that. Now, how can we, sort of integrate them into these two guys? Well, if we're not looking at steric hindrance right now. We're only considering how many carbon atoms are on the carbon-carbon double bond. We refer to this as substituted or substitution. This carbon-carbon double bond has 1, 2, 3, 4 carbon atoms on it, so we would call that a tetrasubstituted. This carbon-carbon double bond has 0 carbons on it, so this would be a non-substituted. This guy has 2 carbons on it, so it would be di-substituted. This guy also has 2 carbons, so it would be di-substituted. So that would make this one, because it is tetrasubstituted, this is more stable. This is di-substituted. This is also di-substituted. And this is not substituted, so that would be the least stable of these 4. So we've got 2 different variables that we're using to predict stability. First, we're looking at how substituted is the alkene. The more carbon atoms that are attached to the alkene, the better. So we've got 4 substituted versus a 2 versus a 2 versus a 1. And if we have a tie, so if we have 2 molecules that are both di-substituted, then what we're looking at is steric hindrance and crowding. Can we get those 2 alkyl groups as far apart from each other as possible in the molecule? So let's take a look at what we're going to do next. We've got 2 more molecules to go. We're going to do 1 propene and 2-methyl-2-butene. 1 propene and 2-methyl-2-butene. So let's use the internet to help us find those structures. 1 propene is carbon-carbon double bond with 1 methyl group on it. So that would look like this. And then the other one, I've already forgot what it was. The other one was 2-methyl, it's down here, 2-methyl-2-butene. 2-methyl-2-butene. Which looks like a carbon-carbon double bond that has 3 methyl groups on it. So we'll draw that over here. Carbon-carbon double bond that has 3 methyl groups on it. And let's add these into our ranking. So here we're really going to be looking at how substituted these alkenes are. We've got a 4 substituted alkene versus a 2 versus a 2 versus a 0. This is a mono or singly substituted alkene. This is a carbon-carbon double bond that has 1 carbon on it. So that means that it's going to be in this spot right here. It's going to be less substituted than less stable than our di-substituted alkenes, but it'll be more stable than this little guy right here. So let's move this one down to the bottom and let's put our mono-substituted alkene right here. And then our last one, we have a tri-substituted alkene. The tri-substituted alkene is going to be more stable than our di-substituted alkenes, but not as stable as this guy right here. So we will move him to the top, and our tri-substituted alkene is going to fit in this spot right there.